All right, so a couple of people sent me an answer, and a couple of people said it's because it has all the numbers from 0 through 9 in it, which is true, but that doesn't make it unique because I could have 1, 2, 3, 4, 5, 6, 7, 8, 9. Got the commas in the wrong spot. Zero. And that would also have all the numbers in it. Let me do something for you. Let me write down what we got. There's an 8. There's a 5. There's a 4. There's a 9. There's a 1. A 7. A 6. An 8. We're looking at the wrong one. 7, 6, 3. 2. And 0. So, anybody see anything else that makes this a totally unique number? You can say it out loud now if you think you got an answer. No one? How about the fact that these are all in alphabetical order? It's the only number to have 0 through 9 in its value that's in alphabetical order. Okay, so that's what makes it special. Okay.
How?
How what?
Alphabetical order? I didn't get that part.
All right, so you got 8, 5, 4, 9, right? So 8, 5, 4, 9. So it's E, then F, and the F's divided, the I comes before the O. So it's 5 before 4. Then N, O, S, S, T, T, Z. So these are in alphabetical order. If you spell out, you write out the words, they're in alphabetical order.
Okay, thank you.
Okie doke. Okay, that's not the one I want. This is the one I want. So last time when we left off, we had this as a problem. And the question was to figure out everything that you could. Let me make this and get rid of all the writing. A couple of people sent me a reply. A lot of people didn't. All right. So if we look at and we think about our table, whoa, got to change that shorter. You had V sub S, R1, R2, R3, R4. You had the resistance, the current, and the voltage. And let's put in what we know. We know that R1 is 1, well, we know that V sub S is 10 volts. Let me just draw a line over here so I can see where I'm at. V sub S is 10 volts, that's all we know about that. R1 has a resistance of 1.3K. R2 has a resistance of 680 and a voltage of 2.464 volts. R3 is unknown and R4 is 560. So If we look at what we know, remember we need to know 2 out of 3 to solve anything. So I only have 1 out of 3, 1 out of 3. Here I've got 2 out of 3, nothing out of 3, 1 out of 3. So from this one, we can solve for the current. So I can say that I sub R2 is V sub R2 over R2. So I have 2.464 volts divided by 680. And if you do that, that works out to be 3.624 milliamps. So we know that this value is calculated to be 3.624 milliamps. How does that help us?
The current is the same throughout the circuit.
The current is the same throughout the circuit. It's a series circuit. That was one of the rules of a series circuit, that it always has the same current. I'm going to do this. I'm going to make this whole column milliamps. That means I can put 3.624 there, 3.624 there, 3.624 there, 3.624 there. I'm reluctant to do that, but I'm going to do it because I didn't have to leave myself enough room. I put milliamps at the top. That means anything in here is now in milliamps. On the exam, fortunately, I'm happy to say most people remembered to worry about prefixes. There were a couple of people who thought about the little M's and K's as decorations and didn't use them and ended up with wrong results. But most people did. And the interesting part was, in one of the conversion problems, there were a couple of people who remembered the prefix for one and then forgot about the prefixes for the next one. And that I don't understand. But anyway. So from here, now we've got 2 out of 3 for a lot. So I could figure out that this does not apply. But we can figure out the voltage here. We can figure out the voltage here, and the voltage here. We can use that to figure out this voltage over here, and use that to figure out the resistance. And there is a shorter way if all you wanted was the resistance, but we'll go through that in a minute. So if I wanted V sub R1 is going to be, oh, and this, by the way, is now my I total. We could say IT times R1. So I've got 3.624 milliamps times 1.3K. 4.71 volts. So this is going to be 4.71 volts, or 4.710 if I want to work the 4 round to 3. V sub R4 is IT times R4. So I've got 3.624 milliamps times 560. .029 volts. So now I can use Kirchhoff's voltage law. We could say that V sub 1, the supply voltage, is V A B plus V B C plus V C D plus V D to ground. So if we plug in numbers, we have 10 volts is equal to 4.710 volts plus 2.464 volts plus VCD, the unknown voltage, plus 2.029. And when you do the math, VCD is going to be 4.710, 10 minus 4.71 minus 2.464 minus 2.029. So this works out to be 0.7970 volts. All right, that's 6, 8, 9 something. Yeah. Okay. So now we've got calculated this to be 0.79070. And now I can just say that R3 is V sub R3 over R3. I sub R3. So we've got 0.7970 volts divided by 3.624 milliamps. So we come up with 219.9 or 220 ohms. The other way to solve it would have been to say, if all we wanted was R3, we could say that IT is the supply voltage divided by RT. Or if I rearrange that, RT is VS over IT. We already figured out the IT, so this would be 20 volts divided by 3.624 milliamps. And that works out to be
I mean, the voltage is 10 volt, right?
Yep, thank you.
Mm.
Thinking of a different problem. Getting ahead of myself. $2.75. Well, when you do the round off to 4 places, it's 2.760. K ohms. So if you take RT is R1 plus R2 plus R3 plus R4, then you can say the 20, I'm going to put this in ohms, 2760 is equal to 1300 plus 680 plus R3 plus 560. You should come up with the same R3 is 220 ohms. Okay. Questions? So that was the homework. Like I said, a couple of people sent me solutions. A lot of people didn't. I hope that that doesn't mean that a lot of people were totally lost, but I got one more for you to do before we get into parallel circuits, which is what I want to talk about today. Where is my... Okay, so there's a 3 resistor circuit. This is not that. This is P sub R1. Let me just check that that's right. Yeah. P sub R1 is 8.864 milliwatts. See if you can solve for all the voltages, currents, and the unknown resistance R3. You're now adding a 4th column to the table. You had the column with resistance, current, voltage. Now you're adding a column for power. Wrong column. Let's take a look at it because there's a couple more things I want to get through today. What can I solve for? Where do I know enough to solve for anything?
For R1, you could try to find the voltage.
Okay, we could do that. So we could say that V sub R1 well, let's do it this way. Let me back up the other way first. We know the power and we know the resistance. So we know that the formula is P sub R1 is going to be V sub R1 squared over R1. So if we rearrange that, we get V sub R1 is the square root of P sub R1 times R1. Right? We cross multiply the R so we get the product. And this is squared, so we take the square root of both sides. Square root of V sub R1 squared is just V sub R1. Square root of P sub R1 times R1 is square root of P sub R1 times R1. So we've got 8.864 milliwatts times R1, which is 180. And we take the square root of that. So times 180. And nuts. Comes out to be 1.263. Okay, if we wanted to find the current, we could say that P sub R1 is I sub R1 squared times R1. So I sub R1 is going to be the square root of P sub R1 over R1. So I've got the square root of 8.864 milliwatts divided by 180. 7.017 milliamps. So this becomes 7.017 milliamps. I'm going to make this all in milliamps. Which means that,
You could do V divided by R too, right?
yeah, the only reason I'm reluctant to do that is, first off, if I do that, then whatever round off error I've got here gets introduced into here. And the second part of it is, if I screw up this calculation, and right off the bat, I guarantee on a calculation like this, somebody in the class will forget to take the square root. They'll multiply these, get so wrapped up in the problem that they'll forget to take the square root. And that would make this wrong, which is going to guarantee that this is wrong. So you always try and go back to given values if you can. Okay. Okay. So we've got all of those. So now we could go through, and I'm not going to go through the whole rest of the problem because we can, the next step would be calculate I sub R2, and then use KVL to find V sub R3, not I sub R2, V sub R2. All right, so you'd find this, because you got two things here. You can find this. Once you know this, you've got everything you need except for one unknown in this column. Kirchhoff's voltage law says the 20 volts has to be VR1 plus VR2 plus VR3. We can find VR3. Once I know that, I can go back and find the value of R3. So use Ohm's law to find the resistance R3. Now, one of the things we didn't talk about, I said before that this is sort of an irrelevant value. It is, but it isn't. This value is RT. It's not the resistance of the source, but it's the resistance that the source sees. So I could say that RT is going to be V sub S over IT, and then use that the total resistance, which we figured out the other day, R1 plus R2 plus R3 equals RT. We could use that as our check. So if I came up with a number over here, if I calculate this using Ohm's law, V sub S over IT, that better add up to this resistance plus this resistance plus this resistance. If the sum of these three does not equal the one that I get by saying V sub S over IT, if this division does not equal this, you've got some sort of an error somewhere. Okay. So we can make that same analogy over here and say that P total is IT times VS. All right. So once I have IT, multiply these two, that gives me my P total. And P total is the sum of the powers of the resistors.
What is VS exactly, like the S?
Supply.
Oh, supply, okay.
Yeah, it's the supply voltage.
All right, thank you.
So it's funny. I just realized I raised my voice because whoever just asked the question, the voice seemed far away, and I'm so used to being in a classroom where if the person is all the way in the back, I raise my voice, and whoever that was, Carl, was that you, Carl? Your voice seems so far back. I don't know if you're away
Yeah,
from.
that was me.
Yeah, I just automatically raised my voice so you could hear me and not realize I didn't have to. Okay, anyway, so if I calculate this power by saying IT times VS, and I add up PR1 plus PR2 plus PR3, that should also equal this value. So one of the other rules you can remember is that the total power is equal to the sum of the powers of the individual resistors. And the other one, I think we talked about this the last time, is that RT is VS over IT. All right, so a couple of rules that go along with that. Okay, any questions on this problem? Like I said, I want to save some time. Maybe what I'll do is I'll finish it up, I'll write it out and post the solution. Let me make myself a note so I remember to do that. Sheet 2. Okay, I'll send that out as an email. Okay, so let's say I had a 3-resistor circuit, and this applies for any number of resistors in series, but we'll do it with 3 because it's easier. So when we had a circuit, if we knew all the values, all the resistances and the voltages, we said that the first thing we would do is we would figure out RT, and that was going to be R1 plus R2 plus R3. And then we were going to find IT would be VS over RT, or REQ.
Sorry. Question, Professor. What's the difference between RT and REQ?
Yeah, as I was writing it, I realized I had been using REQ. So let's make this REQ. The equivalent circuit resistance, here's the reason I don't like using RT, and it's based on a lot of years of experience. RT makes sense when you talk about series circuits. And the way you get the RT or the REQ in a series circuit is you total up all the individual resistors, RT, right? R1 plus R2 plus R3 in this case gives me the book calls RT. When we get to parallel, you're not going to add up the resistances, but my experience has been the minute I write RT, even in a parallel circuit, even though it's a whole different circuit, people will go R1 plus R2 plus R3. Matter of fact, we will have a bet on that on the exam. And I'll explain about bets and exams later on when we get to the exam too. So I really don't like using RT. It's the equivalent of the 3 resistors. And the way you calculate the equivalent is different between series and parallel. And I found that if I use RT, people want to just always add the resistor, whether it's a series or parallel. And so let's just call it REQ. Okay, so we got the REQ, and we've used that to find IT. So now if I wanted VR1, I would just say it's IT times R1. But let me put that in place. So IT was VS over the REQ, which was R1 plus R2 plus R3. So that's my IT, and we want to multiply that times R1. Well, let me ask you a question.
Yes.
I'm getting there. I got to write this first.
T.
Is this the same as this? Mathematically, is this the same as this? Let me put this in the meantime.
Yeah.
There's a middle step. So I think if you look at this and then you take it to the next step, oh, I wrote that backwards. Yeah, okay. You could just, I haven't got right, but this is the three resistors. So the order of multiplication doesn't matter. So I could just write this as R1 times VS over R1 plus R2 plus R3. And then I can just factor out the VS. It turns out that instead of doing 1, 2, 3 steps to get VR1, we can do it all in one step. All right. This is called voltage division. And it's a one-step approach to solving for the voltage across a resistor in a series circuit. So the way we do this is, in the numerator, we put the resistor we want to find the voltage across. In the denominator, we put the REQ as individual resistors, or if you already calculated it, you can just use it. And we multiply that times the supply voltage. So if I wanted VR2, I would say using voltage division, VR2 is just going to be the resistor I want to find the voltage across, R2, divided by the sum of the resistors. Matter of fact, let's make this, yeah, let's leave it the way it is for now. R1 plus R2 plus R3 times VS. And if I wanted VR3, it would just be R3 over this times VS. So let's put some numbers in. Let's say R1 was 680, R3 is 220, and R2 is 1.1 K. And VS is 24 volts. So an example. Let's say we want to find V sub R3 using voltage division. We'd say V sub R3, the resistor we want to find the voltage across, R3, divided by the sum of the resistors in series. Now, obviously, if you had 4 resistors in series, you wouldn't stop at 3. It would be R1 plus R2 plus R3 plus R4. So for whatever number you've got in series, that total goes in the denominator. So in this case, we only have 3. And we're going to multiply that times Vs. So if I plug in the numbers, I have 220 over 680 plus 1.1 K plus 220 times 24 volts. So this is what, 900, 2,000, 220 over 2,000 times 24. .64 volts. So in essence, what we did was we combined solving for RT, solving for the current, and multiplying times the resistor all into one step, one formula to do that. Sometimes you'll see this written as some of the resistances, the REQ. Okay.
Sorry, would you repeat that again? What did you get for your answer, Professor? 2.64?
2.64. Did you not get that?
No. I don't know if I did something wrong.
Well, this is 680, right?
Yeah, that's 6.
680 plus 220
Oh.
is 900. 900 plus 1100 is 2000. So this becomes 220 over 2000 times 24.
I got you. When I was doing my additions in the calculator, I didn't check, and instead of putting a 0, I put a decimal point because, of course. Gotcha. Okay.
It's always the little stuff that gets you.
Isn't it?
All right, let me say this, and this is important, so listen carefully. We now have 2 different ways that we could solve for individual resistors in a series circuit. If I said on the quiz or on an exam, find the voltage across, let's say R2 in this case. Find the voltage across R2. You could go through the process of finding REQ, IT, and then multiplying to get the voltage. That would be fine. You could do voltage division. That would be fine. If, however, on a quiz or an exam, I say to you, like we did here, find VR3 using voltage division, what I'm really saying to you is, show me that you understand voltage division. So if you solve for REQ and then find the IT and then multiply, that doesn't show me anything that you know about voltage division. So if I do not specify a method, you can solve for it any way you want. And this is not a generic rule in class. If I specify a specific method, what I'm really saying is, show me you understand that method. And if you do it any other way, even if you come up with the right answer, it will be marked wrong because you didn't show me that in this case, you understand voltage division. Okay? That clear to everybody? And I'll probably say this about 3 more times before the exam and at least 1 more time before the quiz. If I specify a method, you got to use that method. Even if it's right, if you used another method, you will be marked wrong. Okay?
Speaking of exam, professor, you didn't happen to finish grading ours, did you?
I did, but I have one person that did not take the exam, and I don't want to go over the exam and give out grades until that person has taken the exam.
Oh, okay.
I will say the grade distribution, this group is one of the more unique groups in my experience, in that I actually got a pretty much of a bell-shaped curve distribution for grades, which is usually unique because usually I get an inverse bell curve where I get a lot of people get good grades and a number of people get bad grades and not a lot in the middle. It's like you either knew it or you didn't know it. This class was unique. I actually got, like a bell curve.
What does that mean?
Pardon me?
What does that mean? So like that means a lot of people did bad?
No. If you took and gave, let's say, an exam to a large group of people, what you should get is a curve that looks sort of like that.
Mm-hmm.
The question
This
is,
would be
at what
100.
point does the bell ring?
Yeah, right. So you get a lot of people who, got in a middle range, fewer people at the top, fewer people at the bottom. And like I said, so that says that, you got that distribution. Like I was starting to say before, a lot of times I get this, which says these are the people who studied. These are the people who didn't. And not a lot in the middle. But there were a good number of people who did well and average and above. Let me just put it that way. So
Okay.
overall, I was pretty much pleased with the grades for a first exam for a 112 class.
Okay.
Okay. Any questions on voltage division? Just for a practice problem, solve for, I'm going to have to find a spot over here. Solve for V sub R1 using voltage division. let's take a look at it and see how you made out. V sub R1, if we're using voltage division in the numerator, in the top, we put the resistor we're trying to find the voltage across, that's R1. In the bottom, we put the sum of the resistors. So it's R1 plus R2 plus R3. And we multiply that times V sub S. So we've got 680 divided by 680 plus 1.1K plus 220 times 24. .16 volts.
Yes, sir.
Okay. So let's look at something like this. Okay, for homework. And once you've gotten the problem down, you can head out. Email this to me before class starts on Thursday. So you're going to calculate VBC using voltage division. Calculate the power dissipated by resistor 3. Calculate the voltage that is across from, or, oops, D, that should be VE. That's what I wanted. VE. Calculate the voltage from E to ground.
So just to double check, Professor, for the resistances you have 10K, 6.8K, 1.2K, 12K, and then another 10K?
Yep.
Okay.
Just quick, the answer to the previous problem we did was 8.16, right?
Yes.
All right, thank you.
Can you put that screen before?
All right, take care, Professor.
All right, take care. See you on Thursday.
Thank you, Professor. Have a good one.
Take care.
See you Thursday.
Yeah.
Number 3 up real quick.
Ronnie, you're right. Each number is unique.
Yep. You know that digitally, it's amazing to even grasp it. If you look at the digital file, which is a song or a movie, it's just a big number.
Oh, yeah.
Yeah.
I mean, it's when you come right down to it, it's all this. If you take it all the way down to what's going into the recorder or into the processor, it's all a string of zeros and ones.
Yeah. So so basically, there are people that have copyrights on a single number.
That's true. I hadn't thought about that.
Mm-hmm.
Yeah. Wow. Hadn't thought about that at all.
Okay, I just have a question. Do you know if the material covers in what comes after resistive reactive circuits?
Yeah, reactive.
Is it covered in ENS 225?
You know who would be better to talk to about that? I've never taught ENS 225, but I think Atwood is teaching ENS 225 now.
Okay.
So he might have a better handle on what's in that course.
Okay. So, but has he taught other than lab? Has he taught this course before? So if I ask him about reactive circuits.
Well, he's taught. I know he's taught sections of ELT115, which is the reactive circuits on an algebra trig level, not a calculus level.
Okay. So probably it is covered there.
Yeah.
All right. Thank you. Have a great day.
All right. You too.
Have a good day, Professor.
All right. Take care.
Professor, can you put sheet number 3, please?
What is VE, Professor?
Calculate VE.
Yeah.
The
Oh,
voltage.
VE. Okay, the point. Okay.
Yep.
I thought E stand for something.
No,
Right.
just point E. E
All
to
right,
ground.
Thank you. Thank you. Have a good one.
All right. Yancey, you good or you need more time?
No, I was waiting for the sheet number 3.
Oh, okay. That one?
Yeah. Thank you.
Okay. You all done?
Yeah, I'm good. Thank you.
Okay. See you on Thursday.